Okay, so as Kazi mentioned, we'll talk about the science typically I'm doing, which is water megamasers. My main collaborators are mentioned here. That's Paola Castagna, Gabriele Surcis, and Elisabetta Lado from the Observatory of Cagliari. A brief outline of my talk. Use this one. So I will introduce the water maser at 22 gigahertz in a nutshell, because that's not the focus of the meeting of the colloquium, because I will move to lower wavelengths in a second part of the talk. Indeed, I will introduce which are the main millimeter and sub-millimeter maser transitions in extragalactic objects, and where they have been found so far. So which kind of galaxies and what can we derive from studying them. In the second part of my talk, I will focus on two works which we are leading in Cagliari with my group. That's mainly focused on the galaxy IC485, which is a new disk maser candidate. And the second galaxy is a long name, TXS2226-184, which I will report on a very recent ALMA detection at both 183 and 380 gigahertz. And I will conclude with some consideration about the potential of the existing and upcoming facilities in the framework of the megamaser science. Okay, let's start with telling you about which are the main molecules which are typically found in extragalactic objects. So you may have the OH maser. It's here. You have formaldehyde, which is a little bit, very few cases. A little more popular is the methanol masers. But most of all, we have water megamasers in extragalactic objects, which are by far the most well-studied and the brightest sources. So very briefly, where are they found and what can you do with 22 gigahertz water megamaser? Well, there are some of them associated with accretion disks around supermassive black holes. This is a typical spectrum, which, as you can see, has three groups of features. The systemic ones, which has at velocities very close to the systemic velocity or accretional velocity of the galaxy. Then you have the red shifted and blue shifted features, group of features, that represent the tangential point of the disk. As you can clearly understand, this traces the rotation of the disk, if the disk, of course, is oriented at a proper edge-on orientation. You can derive disk geometry, black hole masses, assuming Keplerian rotation, and with a little more complex single dish and VLBI follow-up studies, you can also derive the distance of the galaxy with an impact on the distance ladder scale. Then you have the jet maser. So this water megamaser are associated with the radio jets in AGN. They are slightly different in shape. You can see up here. You typically have a single broad line, usually redshifted with respect to the velocity of the galaxy. And of course, if you do follow-ups of those, you can study the evolution of the jet and the speed of the material within the jet. There's a third case, which is not very different, but they're mostly tracing outflow, nuclear outflows in AGN. And in this case, again, you can trace the geometry of the outflow. Of course, the outflow has a slightly wider opening angle with respect to the radio jets. Last but not the least, surely, we have also star forming or star formation associated masers that within, for example, the local group can be used to derive proper motion and 3D geometries and distances of the galaxy within the group, with a clear impact on the amount of material, visible and dark, which is in the local group. So everything is very useful. And so far, I was relatively self-confident about the topic because this is what I've been done, as Kazi said, for 25 years. The 22 gigahertz maser line was most my main topic. But now, as you can see from this sketch, I'm moving toward a more risky topic, because millimeter and sub-millimeter masers are very new to me. And I will tell you now, in a part of the talk, why I became interested in millimeter masers. So let's start first with a description or an outline of the levels which are produced by the water molecule. Some of those, the one in black, are what can produce maser emission. The ones circled in red are those which are of interest so far for extragalactic maser studies. You see, there's the 183 gigahertz, the 321 and 324, 5 gigahertz. This is the 22 gigahertz within the centimeter domain. And there is also the 380 gigahertz, which is dashed. And I will tell you in a second why. So most of these masers are covered by the ALMA bands. I recall you, but as I said, I'm not experienced, so please correct me if you think. There's about 10 bands so far with ALMA. And in the band 5 and band 7, you find most of these red circled transitions. We also have NOEMA. NOEMA is well, we all know ALMA is Atacama Desert, many antennas. NOEMA is on the Plateau de Bourg, is the expansion of what was the Plateau de Bourg interferometer. And they have 4 bands. There is a coverage between, it says 80 and 370 gigahertz, but it's of course a discrete coverage. And NOEMA is a very good instrument. The main big difference, apart from the number of bands, which is the frequency coverage, is also in the fact that the NOEMA doesn't have very long baseline configuration or long baseline configuration as ALMA can have. So of course the resolution, angular, and then turns into spatial resolution is not as good as the longest baseline of ALMA. So why the dashed 380? Well, you all know that the atmosphere plays a role in astronomy at different wavelengths, but we are now focusing on the water maser transition. The blue one is the 22 gigahertz bump of absorption by the atmosphere, which is small because this one is the oxygen, which is very, very relevant, but is still affecting the observation because the absorption of the atmosphere plays a role in the signal you receive. And when you go to millimeter, sub-millimeter regime, you get further bands which are actually absorbing your signal, preventing or diminishing the effectiveness of the observation. In particular, the 380 gigahertz is one of the most affected, and this is why band 7 ends at 370 gigahertz, and band 8 starts at 385. It's trying to avoid the 380 absorption band. But luckily, at least on some sides, we have relatively weaker sources because they are far away. But as you can understand, the Doppler shift at least moves the 380 to lower frequency, so we are less affected by absorption. And that's why 380 gigahertz becomes possible also with ALMA. Okay, now I will go for a brief history of what has been found so far in millimeter and sub-millimeter extragalactic water maser science. I divided this more or less in roughly decades, and please don't be scared that I will talk for 2 hours or something. There are relatively few studies done so far in extragalactic objects at these frequencies. We have definitely to mention the first detection ever of 183 gigahertz with a sub-millimeter array and a tentative at 439, never confirmed, in NGC 3079, which is a famous 22 gigahertz water maser galaxy by Liz Humphreys and collaborators in 2005. Let's somewhat kick off the starts of millimeter, sub-millimeter water megamaser science. A very interesting detection is also that from, again, at 183 gigahertz in ARP 220. That's a very famous OH megamaser host, while there's no 22 gigahertz detected there by Cernicharo and Pardo. And this is an ultra-luminous infrared galaxy, relatively different. So you will have AGN and ultra-luminous infrared galaxy. Please keep this in mind. Second decade, 2011, 2020, there are more studies. And one of the reasons is definitely, you can see it here. That's cycle zero. So ALMA came online. So when ALMA came online, of course, the number of sources available to be studied were increasing. Indeed, we have a 321 gigahertz line in Circinus and in NGC 4945. We have also 183 with the Apex. Apex is the single dish telescope, which was actually using one of their ALMA receiver at this frequency at that time. What I will want you to focus a little bit more is on this side. So the lower part is the 325 gigahertz detection in ARC 220, which is again the ultraluminous galaxy I was referring to before, because that's so far, or at least to my knowledge, is the only 325 gigahertz transition detected in an extragalactic object. And the upper part was the first time 380, the one I mentioned before, of course redshifted, was mentioned in this gravitational lens galaxy, where water maser was also detected, and this was claimed, and I fully agree, as a tentative, because this could be also accounted for a baseline effect. So this was reported as tentative, reanalyzed by Stacy in 2020, but still it was not a decisive detection of this line. Last, we go from 2021 to these days. Well, more ultraluminous infrared galaxies detections, more also in AGN. That's a work by Dominic Pesce, who detected 183 gigahertz line in about 12 AGNs. And we have, now we move to a little further, a different topic, because NGC 1052 is not only an AGN, it's a radio galaxy. And this is very interesting, and I will talk to about this later on, because this maser was detected for the first time and studied in a radio galaxy. And this again, our interesting 380 gigahertz line detected with NOEMA this time in a two redshifted gravitational lens. But also in this case, the detection was not as confident as expected, although we reaches up to 10 signal to noise ratio. And it was not confirmed as being a maser, because of course, in order to confirm that it's a maser, you have to derive other features, like for example, the brightness temperature. So you need resolution. In this case, could be thermal emission. Okay, so now this was, to my knowledge, what has been found so far in this field. So it was collected in 3 slides, because it takes a little bit of attention to see all these lines moving. But I think it's interesting that so far this was the only thing done until now. Now we go to a couple of sources of interest for our group, which are studying. I will spend a few words on the 22 gigahertz part, and then I will move to the millimeter part in the second part of the description. So this galaxy IC485 is this, you can see the optical image, is a liner, possibly a CFR2. There was a different classification done, but definitely could be an AGN nucleus. I want you to keep in mind the distance. We are above 100 megaparsecs. The sources I showed before, with the exception of the gravitational lens galaxy, were mostly in the nearby universe. Let's say between 4 to 20 megaparsec distance. We are in a different field in this case. And it was known to host a 22 gigahertz water megamaser, relatively bright in luminosity, and a weak radio continuum, nuclear radio continuum, which tells you more or less that the AGN could be radio quiet, or that some of the emission at the LBI scale is resolved out because of star formation. Okay, that's a very sensitive spectrum with the GBT. There are multi-epochs averaged. And the reason was that while the systemic velocities, if you remember the triple peak of the disk, accretion disk masers, the systemic velocities features were clearly detected, but they wanted to highlight these 2 very weak features. This one is the red shifted one. You can see a bump. Of course, there's a scale effect. This is actually real because we detected that in other spectrum too. And that's possibly the blue shifted feature from the tangential point of the disk. So we did a VLBA map, which was able to detect the radio sorry, the redshifted features and the systemic feature. Unfortunately, at that time, we didn't know about this, and so the setup didn't cover properly the blue shifted. But already from some assumption, if you assume that there is a sort of symmetry between the spots, you can you can put forward the hypothesis that this is a disk in Keplerian rotation, with the redshifted part here, the systemic one, and this possibly, we are actually now following this up in the blue shifted part. And when you have a disk in rotation, which is a John, assuming of course Keplerian rotation, you can derive the mass of the black hole, and you can derive the size of the disk. So the size of the disk is about 0.2 parsecs, and the mass of the black hole is around 10 million solar masses. These values are pretty much consistent with what has been found for other Seyfert-2s and Liner galaxies. And that's a paper recently published by my student Elisabetta Ladu in Cagliari. So what about the millimeter part? Well, there's not very much, but if you recall the Dominic Pesce paper in 2023, he was reporting 12 detections. Well, one of the detection, I didn't point this out before because I wanted to show it here, was actually IC485. And what does the spectrum, the millimeter spectrum, look like, and how does it compare to the 22 gigahertz line? Well, it's shown below here. You see the line of the millimeter, the 183 gigahertz line, and you see the 22 gigahertz line. This is, for most of the old sources, there's a conclusion that the millimeter line is typically much fainter, out to an order of magnitude fainter than the 22 gigahertz water maser line. That's a first conclusion, and that's of course has an effect on the studies you can do at millimeter. I just put this question here because we are working on this, and we probably found a sort of a solution to this. Possibly, this fact that it's much fainter may apply only to disk maser. This is indeed a disk maser, and most of those were disk masers. So keep this in mind because there are also JAC maser, outflow maser, and that the situation may be different. Just to show you, however, if you have a brighter millimeter maser, disk maser, for example, the one detected in Circinus, the distance is much, much lower, 4 megaparsec. We are 122. However, you can do very nice studies of the disk. Indeed, Dominic Pesce did a study. This is the water maser, of course, a sketch of the disk, the accretion disk. And these are the blue features and red features in millimeter frequencies, millimeter wavelengths, sorry. As you can see, they both trace, of course, with the uncertainty reported also, a disk. But the disk of the disk outlined by the 22 gigahertz maser seems to be the inner part, while the outer part, outer radii, you get the different conditions, and probably there are produced the millimeter maser. Of course, as usual, high sensitivity to bring the studies further away and resolution to derive the distribution of the spots is necessary to expand this kind of studies, also including our IC485 galaxy. Okay, second galaxy is I want to mention the collaborators here. That's Violeta Pellizzeri, Elena Banikova. But I really want to stress a really great thanks to Kazi and to the European ALMA Regional Center here, because they helped me really a lot, both in setting up scheduling blocks, adjusting parameters, and a very relevant kickoff of the data reduction. Because I still remember the telecom with Kazi, and we wanted to put a window where we really hoped to find something, and it was a bang, and that was really pushing. Thanks a lot. So this is a 22 gigahertz spectrum. So again, at the previous kind of maser, let's say, very strong. It's so strong that it was detected at 6,000 solar luminosity. Okay, I don't want you to believe that these are the typical luminosities, because when I say luminosity, isotropic luminosity. So that means that the luminosity is assumed to be produced on a sphere. Of course, the maser are most likely beamed objects, but the fact that we don't know the beaming angle, in order to compare the sources, we use the isotropic luminosity. So when you hear about this, and you will hear more, 100,000 luminosities, keep in mind it's isotropic luminosity. It's assuming that it's isotropic. But nevertheless, 6,000 isotropic luminosity, solar luminosity, was the first case where it was mentioned the word gigamaser. Not even megamaser, is a gigamaser. We studied with VLBA. That's a work done by Gabriele Surcis and myself and Paola Castagna. We published, and this was with VLBA. We detected 6 spots. So there was like an arc or linear structure. We derived for the first time the maser absolute position, which is relevant when you want to compare the location. No continuum and no polarization was detected. That's a distribution of the masers, the water masers, the 22 gigahertz water masers. That's actually located close to this knot. This is a radio image, a VLBI L-band radio image of the nuclear region of the galaxy. As you can see, you can, with the absolute position, you can locate the maser spots, which are here. But in order to interpret which is the nature of the source, you have to know where the nucleus is. And the problem is that we don't know where the nucleus is. A classical approach is to say that is in between, where there is a gap between 2 radio knots, lobes, whatever, but is actually not confirmed so far. So in order to go into the position of the nucleus, we acquired also EVN radio continuum data at 2 frequencies. And when you have these results, L band and C band, but what is mostly interesting is that when you have 2 frequencies, you can derive a spectral index. So the dependence of the flux density as a function of the frequency, that's a spectral index in this definition, because the spectral index is alpha. And when you do that, you see that there are values. The centrality is quite high, but you have values which are close to 0. That means flat spectral index. And that's typical thermal or slightly absorbed. You can have negative spectral index, and that is typical of optically thin synchrotron emission. While if you get positive spectral index in this definition, you get an inverted spectrum, which in EGN is typically resembling self-synchrotron absorption, and is telling you, in many cases, where the base of the radio jet is. And that's where the nucleus probably is. These are the maser spots, very small to be seen. And they are located exactly where the spectral index is inverted. So probably that's the nucleus. In addition, is also where H1 optical depth is larger, which is also another hint that maybe we got the nucleus. Okay, we are of course not satisfied, and that's where my jump into millimeter, sub-millimeter really happened. We decided to propose for ALMA observation of this galaxy to detect possibly millimeter, sub-millimeter masers. And also that was band 5 and 6, 5 and 7, and also some high density tracer, HCM, HCl+, which can help you in. I will report only on this, on the maser part of this study. The other one is ongoing. I don't want you to read all this. These are details. The only thing I want you to read is this: is a linear scale of the observation is not the best. It's an intermediate configuration. So in fact, it will have an effect on the interpretation. We can do better than this, and probably we will do in the next cycle if we manage. But our hope to detect something, well, that was astonishing to me. These are the 2 detections, 183 gigahertz and 380 gigahertz. I don't want to say anything about the previous detections, but definitely respect to the two plots I've shown, there's a signal to noise ratio higher than about 100. And so I think this is a sort of a confident and luminous detection indeed. Again, isotropic luminosities of one component, the other component, they reaches up to 100,000 solar luminosity. So again, we really have confirmed that this galaxy may not be exceptional, but definitely is one of the a very promising galaxy. It was a gigamaser at 22 gigahertz, is indeed a gigamaser at 183 and 380. So I would say is a very good result for ALMA. It was published in a letter recently. Okay, even further, I told you that when you have a galaxy in which you have already 22 gigahertz maser and you detect additional lines, you try to do a comparison. And when we did so, that the black one is the 22 gigahertz line, the blue one is the 183 line, and you have the 300 gigahertz line in cyan, magenta, I think is this one. Okay, you see that the profile is somewhat similar, which is a good point because the resolution, as I told you, does not allow to tell you exactly there is a maser emission. Of course, with this kind of light density, I'm very convinced it's maser emission. But in any case, this is a further proof that the profile, this is a maser galaxy, is a maser 22 gigahertz, is indeed maser. So if you have the same profile, is most likely maser also for the other two transition, and they are very bright. This is the first unambiguous detection, as I said, of 380 gigahertz in a 22 gigahertz megamaser galaxy, and also the first, to our knowledge, fake case where the three transitions are all detected in the same objects, with a great impact to study the different excitation conditions for the different transitions. Okay, where is the millimeter emission? Well, is unresolved because of the resolution in a location that is represented here by the dark red cross. The magenta cross, it was to be conservative. There is an absolute position uncertainty in the ALMA measurement that tells you that you have to be careful. But by the centroid peak fitting, and when you have such a signal to noise is relatively good fitting, the position of the millimeter maser is here. So pretty much consistent with the water maser at 22 gigahertz that we have seen before. These are the spots. So if the fact that it's also coincident in position further support the idea that is definitely maser emission. But as I said, there's a caveat. The emission is unfortunately presently unresolved. So we don't have the distribution of the maser to be compared with the other transition. Nevertheless, following a model proposed for NGC 1068, which is a famous nearby galaxy where we have masers, also millimeter masers, by Banikova and collaborators, we tried to sketch a model of how and where the emission should come from and the nature of the maser. And I don't want to understand, this is quite speculative yet. I presented this in 22 at the ABN symposium, that's the proceeding. And we are now working on the model with a little bit more refinement. But what tells this is that possibly that's a jet, the radio jet. That's exactly the zooming of the plane of where the maser spots are. That's a millimeter location, and that could be the torus. The torus, as you know, of course, the AGN are expected to be surrounded the supermassive black hole by these big donuts. I will tell you in a second that this is not a very, very compact donuts probably, but definitely our model points out the possibility that what we are having here is not a disk maser in the sense of accretion disk maser. This maser is amplification of the continuum of the jet made by a structure which is in front of this continuum, and is probably the disk or torus throat. So where the torus becomes the accretion disk. That's our interpretation. As I said, is speculative, but strangely enough, after my presentation at the ABN symposium in Core in 2020, a nice paper came out by Seiji Kameno, who studied another galaxy more closer to us, but which resembles a lot of similarities with Texas 2226. You see the double profile here, broad, is like very similar to the situation we have. And they propose for the longest baseline bond, the C10 configuration, which allows you to map the distribution, something we want to do probably in the next cycle. And when they map the distribution in front of the continuum and they interpret that, they came out with a model which is quite resembling the model we have. Mostly there is the jet, that should be the torus clouds, and the maser are actually amplified by the torus. It's jet-torus interaction. And that's confirmed that probably our past model was sort of reasonable. We have to follow this up, and possibly also helped also them to create the paper they produced. Okay, last part of the talk, very briefly. I talked about megamasers in AGN. What are they used for at 22 gigahertz and even more now at millimeter, sub-millimeter? Well, I think I convinced you a little bit that they are useful to probe the innermost region of AGNs. And in that respect, to understand better the AGN paradigmatic unified model. On the left side, I didn't even put, I'm sorry about that, the reference, but I saw Harry Padovani in 95, I think is like, for me, is in my mind, and I thought it was there. That's a very nice sketch of what could have been the unified model. But more recently, the nice donut, compact, very homogeneous, is probably has to be revised by a more clumpy structure, in which also the transition between the disk and the torus is not clear as possibly was expected here. And in that respect, these are work done on masers by Violetta Pellizzeri, Banikova, Elena Banikova also modeled the maser structure, goes in the direction of this view. So indeed, megamasers studies can help in probing the unified scheme. What are the future perspectives on this kind of science? Well, if you have more sources, that would be nice, because more sources means also statistically relevant studies, a better description of what you are seeing. And indeed, at 22 gigahertz, there's big hopes, because the next generation VLA and the SKA is coming online, especially if the SKA will go to higher frequency too. These are work we have done on measuring the number density of masers which can be detected at different redshift. I did this for SCA Memo, is published in a couple of papers, and is also a next generation VLA science use case. And indeed, I don't want you to read this, it was quite small, but it tells you more or less that there's a hope to detect many more masers with these sensitive facilities. But also at millimeter, sub-millimeter, we have ALMA. ALMA is very sensitive. NOEMA can help in that, in the detection experiment. Probably not in the follow-ups, but definitely. And we have also the LMT, the large millimeter telescope, which I would consider very useful. Of course, has to be accessible, but I think it's promising. But many sources doesn't mean that you can study them in detail. If you want to follow them up, you also need to have resolution. And to have resolution, you have to do it for the 22 gigahertz at centimeters wavelength with VLBI, also possibly in the future from space. Radio Astron, unfortunately, is not available any longer, but there are some VLBI space experiments planned for the future. There's also a sketch that I'm preparing, just mostly tells you as a function of redshift, which kind of studies, given a resolution of VLBI or space VLBI, you can do. And you are limited if you don't expand your baseline to just this dot. While if you have VLBI options or even space VLBI option, you can go and study accretion disk or jet interaction up to a consistent redshift. What in the millimeter, sub-millimeter? Well, there is the long baselines of ALMA. C10 is a configuration. I'm really looking forward to possibly see the data. Millimeter VLBI, there's a global millimeter VLBI array, which is really relevant with new antennas which are coming online. And last, and surely not the least, the Event Horizon Telescope, which all you know for the nice pictures of the M87 black hole or for our galaxy black hole, is going to operate also at frequency, which are useful for millimeter, sub-millimeter masers, and will provide baseline, which are really important for follow the sources up. Summary, it's a lot of writing, but it's more or less just get the idea of this. Extragalactic 22 gigahertz water masers are provide, and hopefully, I'm sure will provide unique information on EGN and also on cosmology, because as I mentioned, if you can get the distances, geometrical distances to a galaxy, you can rescale the H0 value, or at least improve the H0 value. The millimeter and sub-millimeter water maser, well, they are complementing, on some sense, the 22 gigahertz, but on the other sense, they are actually brand new information because they trace and study conditions which are different from the 22 gigahertz and so far unexplored. I presented two cases, IC485. We have seen that when we will manage to get the satellite line can trace the accretion disk at different radii. 22 gigahertz is maybe in the inner part and a millimeter in the outer part. In Texas 2226, okay, already said, we got a very nice detection. I have to admit that. We had 22 gigahertz in the past and we added up 183 and 380. So very promising study for being followed up in order to probe the unified model for AGN. Last slide is just saying what I said just at the end. There are, we need facilities which provide high sensitivity and high resolution, both at 20 centimeter and millimeter wavelengths. Indeed, we are ALMA, NOEMA, as I mentioned, and for the centimeter pulse SKA and next generation BLA facilities, which when working in synergy with the VLBI network, will surely promises a very bright future for megamaser science. Thank you.
Thank you very much, Andrea. First question.
Thanks, Andrea. Okay. Well, before just I mean, the question probably be more strategic, but related to the mass of the mechanism that I've never understood properly. I mean, in order to have a maser, you need the levels that are super thermally populated. And so, what is the mechanism that is the
Allora, there are different mechanisms depending on the transition and depending on the molecule. The main mechanism are radiative pumping. It's called pumping. More or less, you pump up a level in order that you are breaking the Boltzmann equilibrium. And these are radiative, like far infrared emission, or the shocks, radiative collisional, sorry.
But in case of radiative pumping, so you need the photons of that frequency allow you to do this pumping. So this is linked to, for instance, you need the sub-millimeter photons in this case. I mean, a lot of sub-millimeter.
To populate the higher level is not the two levels which are involved. What you do with the pumping is you get like a third level.
Yeah.
And when the photon at that frequency comes in this condition of an inverted population, then it passes and it provocates a cascade, like assuming and then the photon gets amplified along the path which has this incoherent velocity. Indeed, they are like one of the bodies like filaments. So these filaments have the same velocity in the cloud. And when the seed photon is coming and the cloud is in inverted condition, so has been pumped, then you get the amplification. And the longer the path, the brighter in theory is the maser. Then there is, of course, a consideration of saturation versus unsaturation of the maser, but that's a little more complicated.
Do you have any constraint on the vertical structure of this megamaser disk?
Okay. This can be done, of course, only for nearby objects because, as I said, the resolution is crucial. It has been found that the disks are very thin. The best case, of course, is still the best case, which I'm really worried to tell because it dates back to 1995. This is IC485, which they not only traces the thickness of the disk, which has to be very thin, but also a warp in the outer part. What really matters and is also the orientation has to be almost perfectly edge on. But there is a nice paper, I have to mention this, has not been followed up. So probably it was just an idea, but I found a very good idea by Jeremy Darling in 2017. He proposed that also slightly inclined accretion disk can produce maser emission. Of course, with a completely different pattern and a mechanism that you see more or less the back part of the disk, which is gravitationally lensed by the black hole. It's a little complicated, but the geometry is surely an interesting part in the accretion disk masers, but you need a relatively good resolution to do so. There's another galaxy which has been studied almost at the level of NGC4258. It's called UGC3789. There are two nice papers. Actually, the triple peak profile is taken from that paper. It's Mark Reed in 2009 and Jim Ratz in 2010. The co-creators, of course. That's a megamaser cosmology project. I didn't mention because it's more on 22 gigas. It was an outstanding project to get this maser. So Jim Ratz was the PI. So when you put Jim Ratz, you will get a lot of disks.
Yes.
Yes, easy. So you said that it's beautiful that all these new stuff are coming up, but because you want to increase the number, it will be very important to understand that the megamaser to increase the number of detection. So my question is, because I'm ignorant in the field, how many megamasers roughly do you know at the moment?
Okay, well, I can tell you straight
And
away.
the second question is, this megamaser can give you a distance information also? Can you scale what's the distance? How do you do that?
Okay. Good questions. The first allows me to tell about the megamaser cosmology project. Okay, the first megamasers were found mostly in the 80s. And then several telescopes did the detection. But one of probably the biggest one, both in terms of dimension and also was the Effelsberg telescope in Germany. Then, of course, you needed higher sensitivity and a more systematic study. And when the GBT, the Green Band telescope, came online, it gave a real burst in detections, especially led by this megamaser cosmology project. I come in a second on the goals because it's related to your second question. The number of masers so far, roughly, we know about 180 sources. And this would be like very optimistic from the number point of view. But then you have to scale down this number for those which are accretion disks, because some others can be jet maser, star forming maser, outflow masers. So if we just stay on the accretion disk masers, probably 1/4, 1/5 of those. Out of this, you have to find a favorable condition that they are somewhat relatively nearby or strong enough or easy to study. The megamaser cosmology project did exactly this. It was surveying big samples, very large samples of galaxies to find new sources, to filter those sources by the single D spectrum, where it was finding the triple groups of feature that could have been a clear disk, let's say, taking this out and starting with the LBI. And now I come to your second question. I should write up the equations that probably I don't even remember, but if you have one of these nice spectra, I could actually go back to the triple big one. What you do is this: with a single dish, you monitor roughly monthly the spectrum, and you see the systemic velocity, which are moving like soldiers, like this. It's called velocity drift. And this is caused by the acceleration of the rotating disk. The systemic ones are the ones which are suffering the acceleration. The tangential one, red shifted and blue shifted, they don't move so much because, of course, the acceleration is not pointing in the direction toward you. With the LBI, what you do the distribution of all these spots. And you put this in a PV diagram to get if it's rotation, Keplerian rotation. The information of both, shaking a little bit with some equation, gives you a geometric distance to the galaxy. with relatively high accuracy on a poor geometrical base. So it's not linked to the standard candles like C8 or supernova type 1. And this is helping. But the problem that you need a lot of them. So the Megamaser Cosmology project was trying to find and followed up as many sources as possible. And so far they did, the number should be about 8. And this, the more you find, the more you study this up, the better you constrain the H0 derived in this way. And that was the Megamaser Cosmology project idea.
The last question for lunch.
Yes, could you show again that about the first galaxy you were showing
Okay.
Keplerian disk cartoon, let's say.
Okay.
Maybe this is something probably I'm missing about the geometry.
Just stopping when
Yes.
this one or this one,
Yes, yeah.
this. Okay.
Maybe I'm missing something about the geometry of the emission. But if the system is like that, I might expect to have some emission also from material that is in between the green, red, and blue.
Actually not, because the problem is that what is considered question is very, very reasonable. The fact is that the disk is actually not a disk, is a ring, because the inner part, the closest of the disk towards the supermassive black hole, has condition in which probably dust has been sublimated and the molecules are probably not even there any longer. So you have an empty part of the disk. What it remains to you is a ring. And the ring has the continuum in the background from the inner part. So, sorry, I'm the tangential part. So the continuum is this, I amplifying to you the continuum. The tangential part of the disk, assuming this is a disk, are the one with the longest path. So your question is absolutely correct, because probably there is something also in between, which would come out here, but is much, much weaker, because the part of the ring is not neither the tangential, which is the longest path, nor the one pointing to you, because it doesn't have the continuum in the background. And so you are missing possible maser there. So that's why the triple peak comes from. Actually, just to go a little bit further, well, this one is definitely a case which is understudy, but also quite complicated because of the weakness. But in some other cases, there are probably situations in which you don't see one of each. And then you may interpret this as not even a triple peak. You interpret as two peaks, and then you start to think about maybe it's a JAC maser, an alpha maser, maybe it's just you're missing them. But definitely the part in between is probably present, but is very, very weak because of the reasons I mentioned.
Okay, so let's thank Andrea again. If you have more questions, please until tomorrow. Please in the E-Ray Institute on the 4th floor, room 605.
Thank you, Giulio. Thank you.
Molto bello. Io avrei saputo.
Ci sono, sì, sì, infatti. No.